The cosmos is all that is, or ever was, or ever will be. Our feeblest contemplations of the cosmos stir us. There's a tingling in the spine, a catch in the voice, a faint sensation, as if a distant memory of falling from a height. We know we are approaching the greatest of mysteries. The size and age of the cosmos are beyond ordinary human understanding. Lost somewhere between immensity and eternity is our tiny planetary home. And yet, our species is young and curious and brave and shows much promise. In the last few millennia, we have made the most astonishing and unexpected discoveries about the cosmos and our place within it. Explorations that are exhilarating to consider. They remind us that humans have evolved to wonder, that understanding is a joy, that knowledge is prerequisite to survival. I believe our future depends on how well we know this cosmos in which we float like a mote of dust in the morning sky. Those explorations required skepticism and imagination both. Imagination will often carry us to worlds that never were, but without it, we go nowhere. This universe is bizarre, strange, at one point even incomprehensible. Many hours at school are spent learning answers to questions. And as a curious kid at heart, I think it is our duty to question rather in order to find the answers. As children, we used to conjure up many things in our head which I personally thought someone would know the answer to. Mom or dad or the teacher. But guess what? Nobody does. These questions evolved into something that is puzzling, even to the whole of humanity. And still, nobody knows their answer. But it is quite exhilarating to think about these matters because they push you to the end of human knowledge, and you never know what treasure lies buried at the border of our horizon. So let's dive into some questions nobody knows the answer to.
I laughed at all his words. I thought he was a bitter man. He spoke of women's ways.
It is said that fact is sometimes stranger than fiction, and nowhere is that more true than in the case of black holes. Black holes are stranger than anything dreamed up by science fiction writers, but they are firmly matters of science fact. The scientific community was slow to realize that massive stars could collapse in on themselves under their own gravity, and to consider how the objects left behind would behave. Albert Einstein even wrote a paper in 1939 claiming that stars could not collapse under gravity because matter could not be compressed beyond a certain point. Many scientists shared Einstein's gut feeling. The principal exception was the American scientist John Wheeler, who in many ways was the hero of the black hole story. In his works in the 1950s and the 1960s, he emphasized that many stars would eventually collapse and pointed out the problems that possibility posed for theoretical physics. He also foresaw many of the properties of the objects that collapsed stars become, that is, black holes. Stars, in a nutshell, are mostly a large collection of hydrogen atoms which collapse into enormous gas clouds under their own gravity. In their core, nuclear fusion crushes hydrogen atoms into helium, releasing a tremendous amount of energy. This energy, in the form of radiation, pushes against gravity, maintaining a delicate balance between the two forces. As long as there is fusion in the core, a star remains stable enough. But for stars with way more mass than our own sun, the heat and pressure at the core allow them to fuse heavier elements until they reach iron. Unlike the elements that went before, the fusion process of creating iron doesn't generate any energy. Iron builds up at the center of the star until it reaches a critical amount, and the balance between radiation and gravity is suddenly broken. The core collapses, and within a fraction of a second, the star implodes, moving at about a quarter of the speed of light, feeding even more mass into the core. It is at this moment that all the heavy elements in the universe are created as the star dies in a majestic supernova explosion. In accordance to the Chandrasekhar limit as theorized by Subramanya Chandrasekhar, this produces either a neutron star, or if the star is massive enough, the entire mass of the core collapses into a black hole. If you looked at a black hole, what you'd really be seeing is the event horizon. Anything crossing the event horizon needs to be traveling faster than the speed of light. In other words, it is impossible. So we only see a black sphere reflecting nothing. Now, if event horizon is the black part, then what is the hole in the black hole? The singularity. We don't know what it is exactly. The singularity may be infinitely dense, meaning all its mass is concentrated into a single point in space with no surface or volume. The Einstein equations can't be defined at the singularity. All known physics break down here.
This means that at this point of infinite density one can't predict the future. This implies that something strange could happen whenever a star collapsed. We wouldn't be affected by the breakdown of prediction if the singularities are not naked, that is, they are not shielded from the outside. Roger Penrose proposed the cosmic censorship conjecture. All singularities formed by the collapse of stars or other bodies are hidden from view inside black holes. A black hole is a region where gravity is so strong that light cannot escape. The cosmic censorship conjecture is almost certainly true, because a number of attempts to disprove it have failed. Black holes remained large unknown until the 20th century. In 1926, using Einstein's general theory of relativity, a German physicist named Karl Schwarzschild calculated that n mass could become a black hole if it is compressed tight enough. But it wasn't until 1971 when theory became reality. Astronomers studying the constellation Cygnus discovered the first black hole, which ultimately led to the infamous bet between Stephen Hawking and Kip S. Thorne. When John Wheeler introduced the term black hole, it replaced the earlier name of frozen star. Wheeler's coinage emphasized that the remnants of collapsed stars are of interest in their own right, independently of how they were formed. The new name caught on quickly. From the outside, you can't tell what is inside a black hole. Whatever you throw in or however it is formed, black holes look the same. John Wheeler is known for expressing this principle as a black hole has no hair. But as powerful as black holes are, they will eventually evaporate through a process called Hawking radiation. To see how it works, we need to look at empty space. Empty space is not really empty, but filled with virtual particles and their antiparticles, popping into existence and annihilating each other again. But when it happens right at the edge of a black hole, one of the particles will be drawn into the black hole and the other will escape and become a real particle. One way is to realize that the uncertainty principle allows particles to travel faster than light for a short distance. This enables particles and radiation to get out through the event horizon and escape from the black hole. Thus, it is possible for things to get out of a black hole. What comes out of a black hole, however, will be different from what fell in. So the black hole is losing energy. This process is slow at first and becomes faster as the black hole becomes smaller. At the end of its life, the black hole will radiate away with the energy of billions of nuclear bombs in a spectacular explosion. An untold number of black holes are scattered throughout the universe, constantly warping space and time, altering entire galaxies and endlessly inspiring both scientists and our collective imagination. Shining so brightly that they eclipse the ancient galaxies that contain them. Quasars are distant objects powered by black holes a billion times massive as our sun. These powerful dynamos fascinated astronomers since their discovery half a century.
In the 1930s, Carl Jansky, a physicist with Bell Telephone Laboratories, discovered that the static interference on transatlantic phone lines was coming from the Milky Way. By the 1950s, astronomers were using radio telescopes to probe the heavens and pairing their signals with visible examinations of the heavens.
However, some of the smaller point source objects didn't have a match. Astronomers called them
Quasi-stellar radio sources or quasars.
because the signals came from one place, like a star. However, the name is a misnomer. According to
The National Astronomical Observatory of Japan.
only about 10% of quasars emit strong radio waves. Naming them didn't help determine what these objects were. It took years to study to realize that these distant specks, which seemed to indicate stars, are created by particles accelerated at velocities approaching the speed of light.
Scientists now suspect that the tiny point-like glimmers are actually signals from galactic nuclei, outshining their host galaxies. Quasars live only in galaxies with supermassive black holes. Black holes that contain billions of times the mass of our sun.
Although light cannot escape from black hole itself, some signals can break free around its edges. While some dust and gas fall into the black hole, other particles are accelerated away from it, near the speed of light.
The particles steam away from the black hole in jets above and below it, transported by one of the most powerful particle accelerators in the universe.
This time tomorrow, where will
If you were to see a wormhole, it would appear round, spherical, a bit like a black hole. Light from the other side passes through and gives you a window to a faraway place. Once crossed, the other side comes into view, with your old home receding into a shimmering spherical window.
But are wormholes real, or are they just magic disguised as physics and maths?
For most of human history, we thought space was pretty simple. A big flat stage where the events of the universe unfold.
Even if you were to take down the set of planets and stars, there's still something left.
That empty stage is space, and it exists, unchanging and eternal. Einstein's theory of relativity changed that.
It says that space and time make up the stage together, and they aren't the same everywhere. The things on the stage can affect the stage itself, stretching and warping it.
If the old stage was like unmoving hardwood, Einstein's stage is more like a waterbed. This kind of elastic stage can be bent and even torn and patched together, which could make wormholes possible. Our universe is like a big flat sheet, bent in just the right way, and wormholes could connect two very distant spots with a short bridge that you could cross almost instantaneously, enabling you to travel the universe even faster than the speed of light. But wait, isn't that against the first rule of the universe?
So where can we find a wormhole? Presently, only on paper. General relativity says that they might be possible, but that doesn't mean that they have to exist. But they are theoretically possible, and there are different kinds.
we be on a spaceship?
They were the first kind of black holes to be ever theorized.
They describe every black hole as a sort of a portal to an infinite number of parallel universes. A one-way barrier is formed, an event horizon through which anything can enter, but nothing can escape, trapped at the singularity for all eternity.
But maybe there is no singularity here.
One possibility is that the other side of the black holes look like our universe, but mirrored upside down, where time runs backwards. In our universe, things fall into the black hole, and in the parallel universe, where time runs backwards, the mirror black hole is spewing things out like a big bang. This is called a white hole.
Somewhere sailing across an empty
String theory, or one of its variations, is the correct description of our universe. Our universe may have a web of countless wormholes already. Shortly after the Big Bang, quantum fluctuations in the universe at the smallest scale far smaller than the atom, may have created many traversable wormholes. Threaded through them are strings called cosmic strings. Wormholes need something at the center to counter the force of gravity. This is something totally new and mind-boggling called exotic matter, which is unlike particle or antiparticle as it has negative mass. This may already be possible if we can manipulate the superfluid nature of space caused by the creation of matter and antimatter and their subsequent annihilation, causing space to boil. Because of many constrictions such as paradoxes and cause-time dilation, wormholes may be entirely non-existent.
But wormholes still exist in our hearts and obviously one day.
If they ask her to focus on sailors fighting in the dance hall, oh man.
Neutron stars are one of the most extreme and violent things in the universe. Giant atomic nuclei, only a few kilometers in diameter, but as massive as stars, maybe even more.
After the majestic and pretty awesome process of a supernova explosion,
Which forces the electrons to merge into the protons, resulting in neutrons. Tightly packed together, it implodes into the iron core and causes a pretty amazing and dangerous explosion, outshining entire galaxies. What remains of the star is called a neutron star. Its mass is about 1,000,000 times that of the Earth, compressed to an object of about 25 kilometers wide. That is about 1 billion tons in the size of a sugar cube. Light is bent around a neutron star, meaning you can see the front and parts of the back. Their surfaces reach 1,000,000 degrees Celsius. Inside the neutron star, atoms are so densely compressed that when you reach the base, there are fewer and fewer protons, which ultimately turn into neutrons, creating a chain of millions of atoms in the shape of spaghetti or lasagna,
scientists call this phase as nuclear pasta.
which may be the strongest material in the universe. Eventually, beneath the pasta, we reach the core, whose properties are so extreme they are similar to the time shortly after the Big Bang. We don't know what the properties of these atoms are. When they are packed together so densely, the atoms might dissolve into an ocean of quarks called quark-gluon plasma. Some of those quarks might turn into strange quarks, making a sort of strange matter.
Or maybe they don't. We don't know.
Now, strange quarks' nuclear properties are bizarre. They are heavier and, for a lack of better word, stronger. Strange matter might be ideal stage of matter. Perfectly dense, perfectly stable, more stable than any other matter in this universe, and indestructible. But it might be infectious. Every piece of matter it touches might be so impressed with it that it would immediately turn into strange matter too.
So in few words, they are a zombie virus, but a pretty awesome virus.
Some speculation suggests that since they were present at the time of Big Bang, they initially might be the dark matter.
But probably not. However, understanding these quarks today might tell us
About the birth of the universe and why it looks the way it does. Neutron stars also have the strongest magnetic field of any object in this universe. This magnetic concentration forms vortexes and radiate beams from the magnetic poles. Since the poles are not always aligned with the rotational axis of the star, the beams spin like the lighthouse beacons, which appear to blink when viewed from the Earth. We call these pulsars. The detection of these tantalizing signals by astrophysicist Jocelyn Bell in 1967 was in fact the way we indirectly discovered neutron stars in the first place. An aging neutron star's furious rotation slows down over a period of billions of years as it radiates away its energy in the form of electromagnetic and gravity waves. But not all neutron stars die away so quietly. For example, we have observed binary systems where a neutron star co-orbits another star. A neutron star can feed on a lighter companion, gorging on its more loosely bound atmosphere before eventually collapsing cataclysmically into a black hole. While many stars exist as a binary system, only a small percentage of those end up as neutron star binaries, where two neutron stars circle each other in a waltz doomed to end in a merger. When they finally collide, they send gravity waves into space-time like ripples from a stone thrown into a calm lake. Einstein's theory of general relativity predicted this phenomenon 100 years ago, but it wasn't directly verified until 2017, when gravitational wave observatories LIGO and Virgo observed a neutron star collision. Other telescopes picked up a burst of gamma rays and a flash of light, and later X-rays and radio signals, all from the same impact. That became the most studied event in the history of astronomy. It yielded a treasure trove of data that's helped pin down the speed of gravity, bolster important theories in astrophysics, and provide evidence for the origin of heavy elements like gold and platinum. Neutron stars haven't given up all their secrets yet. LIGO and Virgo are being upgraded to detect more collisions. That'll help us learn what else the spectacular demise of these dense, pulsating, spinning magnets can tell us about the universe.
Where you keep your Rolling Stones records, and a friend of Sasha Distel, yes you do. But where do you go to, my lovely, when you're alone in your bed? Tell me the thoughts that surround you.
In the year 1990, a virtually unknown German mathematician named
Theodore Kaluza suggested
a very bold and in some ways a very bizarre idea. He proposed that our universe might actually have more than the three dimensions that we all are aware of. That is, in addition to left, right, back, forth, up, down.
Kaluza proposed that there might be additional dimensions of space that for some reason we don't see yet.
Now when someone makes a bold and bizarre idea, sometimes that's all it is, bold and bizarre. But it has nothing to do with the world around us. This particular idea, however, although we don't yet know whether it's right or wrong,
this idea has had a major impact on physics in the last century and continues to inform a lot of cutting-edge research.
to begin with, we need a little bit of backstory. Go to 1907.
This is a year when Einstein is basking in the glow of having discovered the special theory of relativity and decides to take on a new project to try to understand fully the grand, pervasive force of gravity.
And in that moment, there are many people around who thought that the project had already been resolved.
Newton had given the world a theory of gravity in the late 1600s that works well, describes the motion of planets, the motion of the moon, and so forth. The motion of apples falling from trees, hitting people on the head.
All of that could be described using Newton's work. But Einstein realized that Newton had left something out of the story. Because even Newton had written that although he understood how to calculate the effect of gravity, he had been unable to figure out how it really works.
How is it that the sun, 93 million miles away, that somehow it affects the motion of the earth? How does the sun reach out across empty inert space and exert influence? And that is a task to which Einstein set himself, to figure out how gravity works.
So Einstein found that the medium that transmits gravity is space itself. This idea goes like this.
Imagine space is a substrate of all there is. Einstein said space is nice and flat if there is no matter present. But if there is matter in the environment, such as the sun, it causes the fabric of space to warp, to curve, and that communicates the force of gravity. Even the earth warps space around it. Now look at the moon. The moon is kept in orbit, according to these ideas, because it rolls along a valley in the curved environment that the sun and the moon and the earth can create by virtue of their presence.
The earth itself is kept in orbit because it rolls along a valley in the environment. That's curved because of the sun's presence. This is the new idea about how gravity actually works. Now this idea was tested in 1919 through astronomical observations. It really works. It describes the data.
And this gained Einstein prominence around the world. And that is what got Kaluza thinking. He, like Einstein, was in search of what we call a unified theory.
That's one theory that might be able to describe all of nature's forces from one set of ideas, one set of principles, one master equation, if you will. So Kaluza said to himself, Einstein has been able to describe gravity in terms of warps and curves in space. In fact, space and time, to be more precise. Maybe I can play the same game with other forces, which was at that time known as
The electromagnetic force.
we know of others today, but at that time that was the only force people were talking about. You know, the force responsible for.
Electricity and magnetic attraction and so forth.
So Kaluza says, maybe I can play the same game and describe electromagnetic force in terms of warps and curves. That raised the question. Warps and curves in what? Einstein had already used up space and time, warps and curves, to describe gravity. There didn't seem to be anything else to warp and curve. So Kaluza said, well, maybe there is. There are more dimensions of space. He said, if I want to describe one more force, maybe I need one more dimension.
So he imagined that the world had 4 dimensions of space, not 3. And
Imagine that the electromagnetism was warps and curves in that 4th dimension. Now here's the thing. When he wrote down the equations describing warps and curves in a universe with 4 space dimensions, not 3,
he found the old equations that Einstein had already derived in 3 dimensions. Those were for gravity.
but he found one more equation because of the one more dimension. And when he looked at that equation,
It was none other than the equation that scientists had long known to describe the electromagnetic force.
amazing, it just popped out. He was so excited by this realization that he ran around his home screaming victory that he had found the unified theory. Now clearly Kaluza was a man who took theory very seriously. He, in fact, there is a story that when he wanted to learn how to swim,
He read a book, a treatise on swimming, then dove into the ocean.
this is a man who would risk his life on theory. But for those of us who are a little bit more practically minded, 2 questions immediately arise from his observation. Number 1, if there are more dimensions in space, where are they? We don't seem to see them. And number 2, does this theory really work in detail when you try to apply it if the world turn around us? Now, the first question was answered in 1926 by a fellow named
Oscar Klein. He suggested that dimensions might come in 2 varieties.
there might be big, easy to see dimensions, but there might be also tiny, curled up dimensions. Curled up so small, even though they're all around us, we don't see them.
So imagine you're looking at something like a cable supporting the traffic light. The cable looks one-dimensional from a distant viewpoint. But you and I all know that it does have some thickness. It's very hard to see it though from far away. But if we zoom in and take the perspective of, say, a little ant walking around, little ants are so small that they can access all of the dimensions, the long dimensions, but also this clockwise, counterclockwise direction.
But this illustrates the fact that dimensions can be of 2 sorts, big and small. And the idea that maybe the big dimensions around us are the ones that we can easily see, but there might be additional dimensions curled up, sort of like the circular part of the cable, so small that they have so far remained invisible.
So if we take a look, say, at space itself, we can only show, of course, 2 dimensions on a screen. But anything that's not flat on a screen is a new dimension. Go smaller, 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 and way down in the microscopic depths of space itself. This is the idea. You could have additional curled up dimensions. Here's a little shape of a circle, so small that we don't see them. But if you were a little ultra microscopic ant walking around, you could walk into big dimensions that we all know about. That's like the grid part. But you could also access the tiny curled up dimensions that's so small that we can't see it with the naked eye or even with any of our most refined equipment.
But deeply tucked into the fabric of space itself. The idea is there could be more dimensions as we see them. Now that's an explanation about how the universe could have more dimensions than the ones we see. But what about the second question that I asked? Does the theory actually work when you try to apply it to the real world?
Well, it turns out that Einstein and Kaluza and many others worked on trying
To refine this framework and apply it to the physics of the universe as we understood at that time and in detail it didn't work.
In detail, for instance, they couldn't get the mass of the electron to work out correctly in this theory.
So many people worked on it, but by the 40s and certainly by the 50s, the strange but very compelling idea about how to unify the laws of physics had gone away. Until something wonderful happened in our age. In our era, a new approach to unify the laws of physics is being pursued by physicists all around the world.
It's called superstring theory.
And the wonderful thing is that superstring theory has nothing to do at first sight with the idea of extra dimensions. But when we study
Superstring theory.
we find that it resurrects the idea in a sparkling new form. Superstring theory. What is it? Well, it's theory that tries to answer the question: what are the basic, fundamental, indivisible, uncuttable constituents making up everything in the world around us? The idea is like this. So imagine if we took a familiar object.
Just a candle in a holder. And imagine that we want to figure out what it is made of.
So we go on a journey deep inside the object and examine the constituents. So deep inside, we all know you go sufficiently far down.
Your atoms. We all know that atoms are not the end of the story. They have little electrons that swarm around the central nucleus, neutrons and protons. Even the neutrons and protons have smaller particles inside of them, known as quarks.
That is where the conventional ideas stop. Here is the new idea story. Deep inside any of these particles, there is something else. This something else is this dancing filament of energy.
It looks like a vibrating string.
That's where the idea string theory comes from.
And just like the vibrating strings that you just saw in a cello can vibrate in different patterns, these can also vibrate in different patterns.
They don't produce different musical notes.
Rather, they produce the different particles making up the world around us.
So if these ideas are correct, this is what the ultra-microscopic landscape of the universe looks like. It's built up of a huge number of these little tiny filaments of vibrant energy, vibrating in different frequencies. The vibrating frequency produces the different particles. The different particles are responsible for all the richness in the world around us. And there you see unification. Because matter particles, electrons and quarks, radiation particles, photons, gravitons are all built up from one entity. So matter and the forces of nature are all put together under the fabric of vibrating strings. And that's what we mean by unified theory. Now here is the catch. When you study the mathematics of string theory, you find that it doesn't work in a universe that has just 3 dimensions of space. It doesn't work in a universe with 4 dimensions of space. Not 5, not 6. Finally, you can study the equations and show that it works only in a universe that has 10 dimensions of space and 1 dimension of time. It leads us right back to this
Of Kaluza and Klein,
that our world, when appropriately described, has more dimensions than the ones that we see.
this is an example of something known as Calabi-Yau shape.
Name isn't all that important.
But as you can see, the extra dimensions fold in on themselves and intertwine in a very interesting shape, interesting structure. And the idea is that if this is what the extra dimensions look like, then the microscopic landscape of our universe all around us would look like this on the tiniest of scales.
When you swing your hand, you'd be moving around these extra dimensions over and over. But they're so small that we wouldn't even know it.
All the countless galaxies make up a single giant edifice, obeying the same physical laws and all made from the same types of atoms, electrons, protons, quarks, neutrinos that make up you and me. However, recent theories in physics, including the string theory, are now telling us that there could be countless other universes built on different types of particles with different properties, obeying different laws. Most of these universes could never support life and might flash in and out of existence in a nanosecond. But nonetheless, combined, they make up a vast multiverse of possible universes in up to 11 dimensions, featuring wonders beyond our wildest imagination. The leading version of string theory predicts a multiverse made up of 10 to the 500 universes. That's a 1 followed by 500 zeros. A number so vast that if every atom in our observable universe had its own universe and all of the atoms in all those universes had their own universe, and you repeated that for 2 more cycles, you'd still be at a tiny fraction of the total, namely 1 trillion 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 trillionth. But even that number is a minuscule compared to another number, infinity. Some physicists think the space-time continuum is literally infinite and that it contains an infinite number of so-called pocket universes with varying properties. How's your brain doing? Quantum theory adds a whole new wrinkle. I mean, the theory's been proven true beyond all doubt, but interpreting it is baffling, and some physicists think you can only unbaffle it if you imagine that huge numbers of parallel universes are being spawned every moment, and many of these universes would actually be very like the world we're in, would include multiple copies of you. Well, there are still some scientists who would say hogwash. The only meaningful answer to the question of how many universes there are is one. Only one universe. And a few philosophers and mystics might argue that even our own universe is an illusion. So as you can see, right now there is no argument in this question. Not even close. All we know is the answer is somewhere between 0 and infinity. But you can always count the answer to life, the universe and everything as 42.
Trees swaying in the summer breeze, showing off their silver leaves as we walked by.
Somewhere out there, in that vast universe, there must surely be countless other planets teeming with life. But why don't we see any evidence of it? Well, this is the famous question asked by Enrico Fermi in 1950. Where is everybody? Conspiracy theorists claim that UFOs are visiting all the time and the reports are just being covered up.
But honestly, they aren't very convincing.
But that leaves the real riddle. In the past year, the Kepler Space Observatory has found hundreds of planets just around nearby stars. And if you extrapolate that data, it looks like there could be 500 billion planets just in our own galaxy.
If any one in 10,000 has conditions that might support a form of life, that's still 50 million possible life-harboring planets right here in the Milky Way. So here's the riddle. Our Earth didn't form until about 9 billion years after the Big Bang. Countless other planets in our galaxy should have formed earlier and given life a chance to get underway billions or certainly many millions of years earlier than happened on Earth.
If just a few of them had spawned intelligent life and started creating technologies, those technologies would have had millions of years to grow in complexity and power. On Earth, we have seen how dramatically technology can accelerate in just 100 years. In millions of years, an intelligent alien civilization could easily have spread out across the galaxy, perhaps creating giant energy harvesting artifacts or fleets of colonizing spaceships or glorious works of art that fill the night sky. At the very least, you'd think they'd be revealing their presence, deliberately or otherwise, through electromagnetic signals of one kind or another.
And yet, we see no convincing evidence of any of it. Why? Well, there are numerous possible answers, some of them quite dark.
Maybe a single super intelligent civilization has indeed taken over the galaxy and has imposed strict radio silence because it's paranoid of any potential competitors. It's just sitting there, ready to obliterate anything that becomes a threat. Or maybe they're not that intelligent. Or perhaps the evolution of intelligence capable of creating sophisticated technology is far rarer than we have assumed.
After all, it's only happened once on Earth in 4 billion years. Maybe even that was extremely lucky.
Maybe we are the first such civilization in our galaxy. Or perhaps civilization carries with it the seeds of its own destruction through the inability to control the technology it creates.
But there are numerous more hopeful answers.
For a start, we're not looking that hard, and we are spending a pitiful amount of money on it. Only a tiny fraction of the stars in our galaxy have really been looked at closely for signs of interesting signals.
And perhaps we're not looking the right way.
First, are we alone in the universe?
Yeah.
It may be that aliens have searched the universe for other life,
Right.
and come to Earth and concluded there's no sign of intelligent life here.
Burn.
Okay.
Burn on
so
us.
he might not be considered among the most intelligent out there.
Okay.
Right. So, second, you can't think we're alone once you study how common our ingredients of life are in the universe. The atoms of our body, hydrogen, oxygen, carbon, they're the three most common chemically active ingredients in the universe. We're not made of special stuff. And we're based on carbon. We're carbon-based life, which is an extremely sticky element that makes molecules all across the periodic table.
Yeah.
So if there was any kind of biology upon which you would base on an element, it would be carbon. And we are such an example of that life. Not only that, life got started almost as fast as it possibly could have in the early Earth. After Earth cooled down from meteor impacts that made us, once it cooled down, complex molecules formed. Within 100 million years, life appeared. So you combine these facts and then you look at the expanse of the 14 billion year age of the universe with 100 billion stars in our galaxy and 100 billion galaxies. To suggest that we are the only life in the universe would be inexcusably egocentric.
Maybe as civilizations develop, they quickly discover communication technologies far more sophisticated and useful than electromagnetic waves. Maybe all the action takes place inside the mysterious, recently discovered dark matter or dark energy that appear to account for most of the universe's mass. Or maybe we are looking at the wrong scale. Perhaps intelligent civilizations come to realize that life is ultimately just complex patterns of information interacting with each other in a beautiful way. And that can happen more efficiently at a small scale. So just as on Earth, clunky stereo systems have shrunk to beautiful tiny iPods, maybe intelligent life itself, in order to reduce its footprint on the environment, has turned itself microscopic. So the solar system might be teeming with aliens, and we're just not noticing them. Maybe the very ideas in our head are a form of alien life.
Well, okay, that's a crazy idea. The aliens made me say it.
But it is cool that ideas do seem to have a life all of their own, and they outlive their creators. Maybe biological life is just a passing phase. Well, within the next 15 years, we could start seeing real spectroscopic information from promising nearby planets that will reveal just how life-friendly they might be. And meanwhile, SETI, the search for extraterrestrial intelligence, is now releasing its data to the public so that millions of citizen scientists, maybe including you, can bring the power of the crowd to join the search. And here on Earth, amazing experiments are being done to try create life from scratch. Life that might be very different from the DNA forms we know.
All of this will help us understand whether the universe is teeming with life or whether indeed it's just us.
I would say the things I want to say tonight, but till I can see that you'd really care for me, I will dream.
Matter as we know it, atoms, stars and galaxies, planets and trees, rocks and us. This matter accounts for less than 5% of the known universe. About 25% is dark matter and 70% is dark energy, both of which are invisible.
This is kind of strange because it suggests that everything we experience is really only a tiny fraction of reality. But it gets worse. We really have no clue what dark matter and energy are or how they work. We are pretty sure they exist though. So what do we know?
Dark matter is the stuff that makes it possible for galaxies to exist. When we calculated why the universe is structured the way it is, it quickly became clear that there is just not enough normal matter. The gravity of the visible matter is not strong enough to form galaxies and complex structures. Stars would more likely be scattered all over the place and not form galaxies. So we know there is something else inside and around them. Something that doesn't emit or reflect light. Something dark. But besides being able to calculate the existence of dark matter, we can see it. Kind of. Places with a high concentration of dark matter bend light passing nearby. So we know there's something there that interacts with gravity.
Right now, we have more idea about what dark matter is not than what it is.
We know dark matter is not just clouds of normal matter without stars, because it would emit particles we could detect. Dark matter is not antimatter because antimatter produces unique gamma rays when it reacts with normal matter. Dark matter is also not made up of black holes, very compact objects that violently affect their surroundings, while dark matter seems to be scattered all over the place. Basically, we only know three things for sure.
1. Something is out there. 2. It interacts with gravity. 3. There is a lot of it.
Dark matter is probably made up of a complicated exotic particle that don't interact with light and matter in a way we expect. But right now, we just don't know.
Dark energy is even more strange and mysterious. We can't detect it, we can't measure it, and we can't taste it.
But we do see its effects very clearly. In 1929, Edwin Hubble examined how the wavelength of light emitted by distant galaxies shifts toward the red end of the electromagnetic spectrum as it travels through space. He found that fainter, more distant galaxies showed a large degree of redshift. Closer galaxies, not so much.
Hubble determined that this was because the universe itself is expanding.
The redshift occurs because the wavelengths of light are stretched as the universe expands.
More recent discoveries have shown that the expansion of the universe is accelerating. Before that, it was thought that the pull of gravity would cause the expansion to either slow down or even retract and collapse in on itself at some point.
Space doesn't change its properties as it expands. There's just more of it. New space is constantly created everywhere. Galaxies are tight-bound clusters of stuff held together by gravity, so we don't experience this expansion in our daily lives. But we see it everywhere around us. Wherever there is empty space in the universe, more is forming every second. So dark energy seems to be some kind of energy intrinsic to empty space. Energy that is stronger than anything else we know, and that keeps getting stronger as time passes by. Empty space has more energy than everything else in the universe combined.
We have multiple ideas what dark energy might be.
One idea is that dark energy is not a thing but just a property of space. Empty space is not nothing. It has its own energy. It can generate more space and is quite active. So as the universe expands, it could be just that more and more space appears to fill the gaps, and this leads to a faster expanding universe. This idea is close to an idea that Einstein had back in 1917 of the concept of a cosmological constant, a force that counteracted the force of gravity.
The only problem is that when we try to calculate the amount of this energy, the result was so wrong and weird that it only added to the confusion.
Another idea is that empty space is actually full of temporary virtual particles that spontaneously and continually form from nothing and then disappear into nothing again. The energy from those particles could be dark energy, or maybe dark energy is an unknown kind of dynamical energy fluid or field which permeates the entire universe but somehow has the opposite effect on the universe than normal energy and matter. But if it exists, we don't know how and where or how we could detect it. So there are still a lot of questions to answer. Our theories about dark matter and dark energy are still just that, theories.
On one hand, this is kind of frustrating. On the other, this is frontier science, making it very exciting.
It shows us that no matter how much we feel we're on top of things, we're still very much apes with smartphones on a tiny fragile island in space, looking into the sky, wondering how our universe works.
There's so much left to learn, and that is awesome. Either answer, in its own way, is awe-inspiring, because the fact that we think and dream and ask these questions might yet turn out to be one of the most important facts about the universe. And I have one more piece of good news for you. The quest for knowledge and understanding never gets dull. It doesn't. It's actually the opposite. The more you know, the more amazing the world seems. And its crazy possibilities, the unanswered questions that pull us forward. So, stay curious.